Hello students, welcome to this MOOC course on advanced analytical techniques. So in continuation of our previous talks where we talked in detail about the Van Demeter equation, let's start the optimization of column, because we have to do certain optimization to get the best results from our column. So in this series of lecture, we are going to study that how we are going to maximize our separation, that is how we are going to effectively separate the different components of a mixture in terms of the equilibration with regard to the different plates that are already imaginary plates that are called as theoretical plates, and we are going to explore the certain insights. So in this series of talks, we are going to study the key parameters, that is we are going to study efficiency, we are going to study the selectivity, we are going to study the retention factor, and of course the most important one is the resolution. So now we actually aim to have a best ever quantification, to have a best ever separation by optimizing different conditions, and we are going to see that how this resolution is dependent upon the efficiency and this selectivity alpha and this retention factor k. We know that selectivity, or if there are two components, for example if we have a two component mixture, then selectivity can be defined in terms of kb upon ka, where kb is the distribution constant of solute B and Ka is the distribution constant of solute A. Now this B is that solute which is going to have a maximum interaction or strong interaction with the stationary phase. So this is how we are going to study it. Similarly, we are going to study the efficiency in terms of the retention factor. So what we can see at this point of time is that the resolution is actually a function of the efficiency, that is N, the selectivity, that is the alpha, and of course the retention factor, that is the K dash. Now we are going to study these three parameters one by one in detail, and we are going to see that how we can interplay with these factors, that is N, alpha and K dash, to obtain the best column performance. Okay. So why optimization is to be done? Optimization is very important because it actually gives you accurate results. It gives you the results which are reproducible. For example, if you are going to separate 5 times, 6 times, 10 times or 20 times, every time you have to have the same results. That is called as the reproducibility. So we have to have reproducibility, we have to have accuracy of our constituent separation. Similarly, we have to ensure that there will be no overlapping of the peaks. That is, your peaks coming out should be well separated from the baseline. It is not like that your peaks like this. This type of peaks actually tells you that your column is not optimized. Column is not optimized. That is, your column is not working effectively. Similarly, we have to look into the coelution. We have to ensure that there are no extra peaks are coming, that is no ghost peaks are coming. And similarly, we have to ensure that there is no peak tailing, that is your peak must be like this. If it is coming like this, then that is called the tailing. So we have to have minimum tailing or at least no tailing. Similarly, we have to ensure that while undergoing certain analysis, certain practical analysis, we have to ensure all these factors, that is the peaks must be well separated, there must be no coelution, that is the peaks does not overlap onto each other, there must not be additional peaks, and of course there must be fronting or tailing. So we have already know that the RS actually, that is the resolution, must be 1.5. with regard to the baseline separation. Similarly, let us consider a case to understand more about this. For example, if we have a chromatogram like this, and we have a chromatogram like this. Now, for example, here you can see that RS is equal to 0.5. Here RS is equal to 1.0 and here RS is equal to 1.5. Now, in all these three different scenarios, that is scenario A, scenario B and scenario C, you can see that this is the RS which is telling you about the overlapping of the peak. And if you have this type of, for example, system, if you have this type of system, you cannot quantify your components. You cannot quantify your components because you have a common area here. And if you have a common area, you cannot have a pinpoint quantification of your different constituents. Similarly, here if you draw a baseline, then again there is some overlap, although not as big as in the first scenario, but again there is overlap. Similarly, in the third case, you have a very clear-cut separation, and this actually RS gives you a very good idea, and this RS is a dimensionless quantity and it gives you an idea about the perfect separation, about the perfect distance between the two peaks. So greater the distance, greater will be separation, and the best the column performance, that means your column is actually optimized. Now let us have a quantitative idea about resolution, that what resolution, how we are going to calculate the resolution in a practical chromatogram. Let us suppose a two-component system. Let us suppose a two-component system 1 and 2. Now this resolution may be, in simple words, it may be defined as the distance between the two adjacent peaks. So let us draw a chromatogram to have a better idea about the resolution. For example, on the x-axis we plot detector response, and now we are going to plot it. Initially we get the peak due to the mobile phase only, then we get peak 1, peak 2. Okay, so this is peak 1 component 1, peak 2 component 2. Now you can see that they are well separated. Let us draw perpendicular. Okay, perpendicular here, perpendicular here. This is the time. Okay, time on the x-axis. This is half of this distance. Let us draw perpendicular here. This is called as half of this. It is called as Tm. From here to half of the peak 1, it is called Tr1. Distance from here to here, it is called Tr2. Okay. Now let us draw perpendicular. So this whole distance is W1. This whole distance is W2. Okay. Now this half of this distance is called as W1 of half, and half of this distance is called as W2 of half. Now this distance, that is called the resolution, let us depict it by delta Z. Now by simple logic, delta Z may be defined as this distance, this whole distance Tr2, this whole distance Tr2, Tr2 minus Tr1, because we have to calculate this distance. This is whole is Tr2, this whole is Tr2, and this is Tr1. So Tr2 minus Tr1 upon this distance, we know it is W1 half, and this distance is W2 half. So what we do, we just add W1 of half plus W2 of half. Just solving it simply, it becomes Tr2 minus Tr1 upon W1 plus W2 upon 2. Now bring it 2 to the numerator side, it becomes twice of Tr2 minus Tr1 upon W1 plus W2. Okay, so this is nothing but this is this relation, that is retention time of solute which is eluting at a later time, that is that solute which is having a strong interaction with the stationary phase minus the retention time of that solute which is having lesser interaction upon width W1 of peak 1 and plus width 2 in the denominator side. So this is the simplest relation, and delta Z can be replaced by simple Rs, that is the resolution, that is the distance between the two adjacent peaks. Now practically how we are going to equate it with the real chromograms, so there we have summarized it. For example, if Rs is less than 1, we have seen in the previous slide, then we get the overlapping peaks. If Rs is 1, then we have partial overlap, and if Rs is greater than or equal to 1.5, we have a perfect baseline separation, because you can see that if you draw this, you can also consider this baseline. You can consider this baseline. You can consider this as a baseline. That is, they are separated from the base. That is, there is no actually overlap at this region. No overlap. Okay. So this is actually how you can quantify your resolution time with the real situations. So what we have to do for an effective separation, the optimization is to be done in such a manner that Rs must lie between 1.5 or greater than 1.5, so that we can have a good peak separation, or that actually tells you about the peak purity, that is your sample is actually contamination free or it is free from impurities. That is, this is how resolution actually works. Now another expression to explain the resolution in terms of three quantities, that is the efficiency, this N is efficiency, L is again the selectivity of the column, and K dash is the retention factor. So we have generated an expression that is 1 upon 4 delta N upon 1 plus K dash, that is the retention. Now this column efficiency we can calculate it, N is equal to L upon H. Similarly retention, it can be calculated, K dash can be calculated, it is Tr minus Tm upon Tm. In the previous slide we know that Tm is the void time, that is the time where the solute does not interact with the stationary phase, it elutes just in one go, that is called the Tm. Tr is the retention time. For example, if it is more than one component system, then we can have Tr1, we can have Tr2, and so on and so forth. Similarly, we have selectivity. When another important factor, selectivity may be defined as, for example, it may be defined as K dash of B upon K dash of A, that is in terms of the retention factor. It can also be given in terms of capital KB upon capital Ka, that is the distribution constant. Distribution constant. It can also be defined in terms of distribution constant of B, of component B, of component B upon distribution constant of component A. Now one thing which you have to keep in mind, that B is that component which is having a stronger interaction with the stationary phase, and because of the stronger interaction it is going to elute at a later time. So initially the first component which is elute is A, and then the last component which is going to elute is B. So your selectivity is described in terms of KB upon Ka or K dash B upon K dash A. So what is the important thing, that by enhancing alpha we can have a more effective, you can say, optimization rather than simply by increasing N. So this we are going to see in the coming slide, that how these factors actually interplay, that is N, column efficiency, retention factor, and the selectivity. Okay, so another expression to calculate N, that is N can also be described in terms of theoretical plates, that greater the number of theoretical plates, greater will be equilibration and greater will be the column efficiency. And another expression is N can be defined as 16 TR square upon W square. So this is actually a formula to calculate the number of theoretical plates for a given practical column. We will solve certain equations, certain expressions, certain problems using this expression, that is 16 TR upon W square. So we have to keep this in our mind. So what actually N tells you, that greater the number of N, greater the number of theoretical plates, then we have narrower peaks. We have narrower peaks. That is, narrow peaks means better resolution, because here the bandwidth or bandwidth is minimum, and that actually implies better resolution. So, and we have already seen when we were discussing separately A, B and C of the parameters of Venn diameter equation, that particle size is very important. Flow rate, we have already seen its importance. Temperature and packing. Packing is governed by lambda and gamma. If you increase your number of plates to, for example, 100 to 110%, then you will get an increase in RS, that is the resolution, to up to 5%. And out of three parameters, that is N, alpha and K dash, we are going to see the effect of each one in the detail, okay, in the coming slides. So we are going to see certain graphs which show the effect of the column efficiency on the peak sharpness. We will be having a comparative diagram, okay, in the coming slide. So retention factor, we have already know that it can simply be given in terms of TR minus TM upon TM, where TM is the dead time and TR is the retention time, which tells you about that what is the interaction, that how strong your interaction of your solute molecules with the stationary phase. So the range we have calculated, we have estimated a range from a given data, and that K is found to be, it should lie between 1 to 10, because K is again a dimensionless quantity, K dash. So for an effective separation, for an ideal separation, or for the best optimization, its value should lie somewhere in between 1 to 10. If the value of K dash is small, then we have poor separation. Again, a very important thing is coming up, and that is, if we have a high value of K dash, then we have a long run time. Still, we have not discussed about the time. Time is money, we know that, and same is the case with the column separation. We are going to study the effect of time, that why time of separation is important. Sometimes it becomes more important than any other factor. So we will discuss this time in detail. Now, for example, for an optimized column performance, your K dash must lie somewhere between 2 to 5. And you have to keep in mind that, for example, consider a case where you are getting peaks. Consider a case where you are getting peaks. Now here you can see the time, actually in the second case, the time is taking the resolution, although resolution is not good, and it is taking too much time. So you have to discard those type of separations. So for an effective separation, the time is very important. So time is to be optimized. Time is to be optimized for effective separations. Okay, so the best time is again 2 to 5 minutes, or not minutes, actually it is a dimensionless quantity, that it should lie between 2 to 5. Okay, for example, for the separation of certain impurities, a drug, the optimized k dash is 3.2. That is an ideal system. Okay. So we are going to study, that is again n, k dash and alpha. Okay. That is the selectivity factor. Now selectivity factor, as we have already know that it is simply a relation, is simply a fraction of k2 dash upon k1 dash in terms of the retention factor. If you want to have in terms of dissociation constant, you can write of k of 2 upon k of 1. That is, 2 is that component which is eluting at a slower rate, that is whose peak is coming at the end of the chromatogram. So for an effective separation, alpha is always greater than 1. This 2 is also implying that the second component is interacting strongly with the stationary phase as compared to have 1. That 2, component 2, it implies that component 2 is strongly interacting with stationary phase and eluting last. Similarly, K1 is implying that component 1 is strongly interacting, it is strongly interacting with mobile phase. It is strongly interacting with mobile phase and eluting fast. That is how actually you define the selectivity factors for a two component system. Now the important things, the most important thing at this point of time which we have to keep in mind, that out of the three factors, that is n, k dash and alpha, the most important thing is here. That is, even in a very small change in alpha can have a large impact on the resolution, because this is alpha which changes the resolution in an exponential manner, not in a linear manner, but in a exponential manner. That is, we are going to see like this, in a exponential manner. A very small change can change it to a very high extent, that resolution changes appreciably. Okay, for example, a very practical example is seen here. Just 1.05 to 1.1 make the resolution just double. You can understand a fraction, it doubles the resolution. So now the question arises that on what factors this your selectivity factor actually depends. It depends upon the stationary phase polarity, because it is the interaction with the stationary phase. Similarly, the interaction with the mobile phase, the pH. For example, if you have an acid-base system, then pH comes into play, because the moment you increase the H plus ions or OH minus ions, it will have an effect on the separation of different components. Similarly, temperature is very important. We are going to see this effect of temperature in the gas chromatography, that how actually the temperature becomes so dominant. Okay, so but the only thing we have to keep in mind, again I am emphasizing it because it is very important, that is a small change in alpha can have a very big implication on the resolution. So let us move forward and have a combined relationship. This is the one of the very dear graph to me, very dear graph. Now this is a 3D graph, and this gives you a relation. This is a 3D graph, and it gives you a relation between the resolution with respect to alpha and resolution with respect to k. So it gives you a clear-cut picture, a clear-cut relation between n, between alpha, and between, of course, the k. So you can see that this selectivity and retention are, they are actually moving in a linear way. But if you think in terms of selectivity with regard to the resolution, they have exponential growth. Okay, they have an exponential growth, which we have already talked. So RS can be defined simply in terms of expression under root of n upon 4 into alpha minus 1 upon alpha into k dash upon 1 plus k dash. So in That is, the efficiency can be improved with regard to the improve in the peak sharpness. Selectivity, again, it shifts the peak positions, and the retention, it tells you about the peak balance spacing. That is how much is the spacing are there. So this graph actually tells you the whole story with regard to the, you can say, the relation between the selectivity and retention, which is increasing at a linear rate, and the selectivity with regard to resolution, which is increasing in an exponential manner. Okay, so exponential manner, that is, it is having a very high effect. A simple change, we have seen that just by increasing from 1.05 selectivity from 1.05 to 1.10, the RS was doubled. We have seen it, it gets doubled. Okay, so now comes the best figure, which gives you a clear-cut idea. These gives you a clear-cut idea about the three factors. Number one is the N, number one is the alpha, and the K. So let us make alpha constant. Here we have make alpha constant, and for example, this is figure A, this is figure B, and this is figure C. Now in figure A, what you have made alpha constant, that is selectivity constant, and on varying N, what you get sharper peaks. So initially your efficiency was compromised, and by the moment you change N, the moment you increase the number of plates, you increase, you get a very good separation. That is resolution. You get a very good separation. You can see low N, that is here the number of peaks, here the number of theoretical plates was this in the red dot lines, and here in the green lines you have sharp peaks, and these sharp peak arises because now you have increased the number of plates. Similarly, in figure B, you have made the number of plates constant. Now by just varying alpha, that is the selectivity, what you are doing, you are actually separating your peaks. That is, you are resolving your peaks. You are actually resolving your peaks in a very beautiful manner. Now earlier, the red line was the earlier, that is when you have a low alpha, that is the low selectivity. The moment you increase the selectivity, the peaks separate. You can see the green one, they are well separated. Here RS, may like say RS of green, and this is RS of red. RS of red. Now you can see that RS of green is greater than RS of red. That is, now the peaks are separated, are well resolved. Okay, well separate. That is, you have optimized your column. Similarly, here again you have optimized your column. Now with regard to last one, again you have made the two factors constant. Initially in the A, you made alpha constant, then you made N constant. Now in the third one, you make two things constant simultaneously, that is alpha and N. Okay, you made two constant. Now varying K, that is the retention factor. You can see that the moment you change it, the corrector spacing changes. You can see that a shift in the peak. Although they were resolved earlier also, but they are now shifted. Okay, that is, initially you were having an early illusion. Now the moment you increase that K dash, you have a delayed illusion, and the spacing remains the same almost. The spacing in fact increases a little bit. That is, resolution is more. That is, it is optimized now. So what are the different strategies by which we can do the optimization? First is the efficiency optimization. Now we have already discussed it, that as far as possible we have to use smaller particles, as small as possible, so that we can we can minimize the eddy diffusion, and also we can minimize the C part. That is, we have to use smaller particles, and we have to use longer columns. Now this longer column is a little bit controversial. This is actually a little bit controversial, because the longer column actually leads to longer separation times. We are going to study this in a very fine manner, that how we are going to optimize by taking longer columns and keeping the analysis time short. So this is a very tricky thing. We will be discussing this tricky thing in the coming slide. So at this point of time, what we have to do, we have to take smaller particles. Smaller particles get very efficiently packed. They are very packed efficiently, and because of the very efficient packing, now lambda and gamma can be minimized. And once you minimize them, the total, that is A plus B upon U plus Cu, can be minimized, and the H can be minimized. And the moment you H minimize, you will have a better resolution. So efficiency optimization can be done by using the smaller particles. You have to use smaller particles as small as possible, so that you can have a very good uniform packing. Similarly, selectivity optimization, you have to modify stationary phase so that it can have a interaction that is appropriate. It is not going, the solute molecule is not going to interact for too long. That is, elution will not be too delayed, or it will not be too fast. Similarly, you have to adjust the pH in case of acid base, or in case of, you can have the charges are involved, so you have to adjust the pH. Similarly, you have to look into the temperature also, because temperature is also very important with regard to optimization. The third thing is the solvent composition of gradient. That is, with regard to, you have to select your mobile phase with regard to polarity, with regard to the combination. That is, you have to have that age old theorem, that is like dissolves like. So you have to keep that which type of stationary phase you are using, the nature of stationary phase, and the solvent. So you have to have a polar combination, or you have to have non-polar combination, that is preferred, but vice versa is not preferred. If you are using stationary phase polar, then you have to employ a mobile phase which is polar. If you are using stationary phase as non-polar, then again you have to use a non-polar mobile phase. So the golden rule is that initially you have to optimize this, because this is actually the hero of all these three. This is actually the hero, that alpha, because a small change in alpha can lead to a change in resolution to many times, many folds. Then comes the second one, the K dash, okay, and lastly the N, because N is a little bit controversial, because here we have to, the moment you increase the number of theoretical plates, because of increase in theoretical plates, the time also increases. So you have to keep an eye on the time also. Okay. So now, effect of selectivity. We have already discussed it. Selectivity is the most powerful factor. Selectivity is most important because it influences the resolution manifolds. A simple change, we have already seen it by taking an example. A simple change influences is too much, because here the resolution and selectivity have a relationship of exponential form. It is not a linear relationship anymore. It's an exponential relationship. Okay. So that actually alpha can be adjusted by having the mobile phase adjustment in terms of composition. Similarly, we have to look into the stationary phase chemistry, that which type of stationary phase you are using, whether you are using alumina, whether you are using some resin. So you have to keep this in mind. You should know the stationary phase chemistry, okay, so that you can actually predict, or you can have an idea about the possible interaction of your solute molecules with your stationary phase. Okay. Similarly, the third one, that is temperature and pressure. Again, you should know that what is the optimum temperature where you can get the best optimization of your column performance. That is how you are going to have the best column performance. Similarly, an example is the amino acid separation, because you know that in amino acid we have a charge separation, and because of the charge separation is there, the pH comes into picture. So this pH actually decides the resolution. Now you can see that in the graph, you can see that alpha increases, and because of the increase in alpha, the resolution is plotted, and here selectivity is plotted, because of a simple increase from 1.25 to the resolution is here, somewhere here. This red line belongs to me, and blue is the original line. So at just 1.25, your resolution becomes 3 times. At simple, you can say that at 1.5, your resolution becomes around more than 5 folds is there. Okay, because you can see So this alpha actually dictates the whole resolution part. This is the most dictating feature. This is the most dominant feature out of all, that is n, alpha and k dash. So alpha is the most dominant one. So we have to keep a very special eye on the alpha, because if we want to optimize our column, first of all we have to look into the optimizing of alpha. And what are the factors? The factors are there, that is the mobile phase composition, the stationary phase chemistry, and the temperature and pressure. Okay. So effect of retention factor. Although retention factor is not as dominant, but still it has some say in it, and that is that, or moderately increase it, it improves the resolution, but not as high as alpha. Okay. So it actually, if it is very small, then it leads to insufficient separation. Similarly, the trick is that you have to keep k dash, that is the retention factor. Again, I am writing it again, that is retention factor is Tr minus Tm upon Tm. That is the retention factor. So you can see that up to a certain limit it is important, but after that it becomes almost constant. You can see that this part. Up to this point, it is increasing in a very steep manner. It is increasing in a very steep manner. You can see in just a matter of 2.5 retention factor k dash. So, but after that, that increase is not very steep. Here the increase is not very steep, but after 10 this almost becomes constant. So it is not as dominant as the alpha. Now the efficiency. So efficiency, n can be directly proportional to column length or the particle size. So the moment you increase n, you actually increasing the length of the column. So you are increasing the number of theoretical plates. So if you double your n, if you for example, if you have a 100 plate system earlier and you increase it by 200, then this will increase to only 1.4% resolution. So again, this is not affecting very much. The efficiency is not playing too much role in optimization. The main player is the alpha, because if you double it, then it will going to increase only 40%. But in earlier case, when you increase it just by a difference of 0.5%, it is going to get doubled. So alpha is the deciding factor. And of course, sometimes on increasing end you have a back pressure also. So number of theoretical plate, it increases, it is very high in case of GC and HPLC. But there actually you have restricted your time. So you have to make fine tuning with the number of theoretical plates with the time also. So let us have a comparative idea about the three things that we have discussed, that is the efficiency and the selectivity factor alpha and the retention factor alpha. So how they are actually affected, let us see. That is, they can be controlled by controlling the column length, or by increasing the column length, or by decreasing the particle size. Okay. So effect, what is the effect on the resolution? Effect is moderate, not too high. That is the increase in the column length and decrease in particle size. That is, the moment you decrease the particle size, you have effective columns, you can say packing, and the column length you are increasing, that is you are increasing the number of theoretical plates, but the effect is moderate. The practical issue is the limited by time. Now the moment you increase the column length, it is good to see that you are increasing the column length, but at the same point your time actually becomes too high. So you have to restrict the time also. With regard to alpha, this is the principal player. This is the principal player of all these three, and it can be controlled by mobile phase and the pH, and its a small effect in the value of alpha has a very large implication. That is, if it changes the RS very high. So practically this is the best option. This is the best thing to optimize. Initially you have to optimize the alpha, then you have to optimize the retention factor, and lastly the n. So if you are going to have a comparative idea, then this one takes the first place, this one takes the second place, and this one takes the third place. So the priority is the alpha, the second priority is the flow rate, and the third priority is of course the n. So you have to have balance here, and the best option is again the mobile phase or the alpha. Okay, so this is how actually these things comes into play, and the best thing is to do the selectivity optimization at a first place. Okay, so with this, thank you students for your patience hearing. Thank you.